Okay, so differentiability. So you guys have studied what is continuity, right? So now we will be doing differentiability. So what is the definition of differentiability? So first thing is differentiability is defined at a point. Okay, it is defined at a point. That is, if I take some point, say x equal to a, and I want to check if a function is differentiable at this point or not. So what I will do is, on the number line, I will approach this point from two different directions. That is from the negative side and from the negative side and from the positive side. And if for both the sides I get the same value, then I will say that this is differentiable. Otherwise, I will say that this is not differentiable. Okay. So this is the whole concept.
Recording in progress.
Okay. So at any point, let's say x equal to a, I will find the left hand derivative, which is if it's equal to right hand derivative, those should be finite and equal, right? Finite and equal. Then we say that function fx is differentiable at x equal to a. That is the whole concept. Okay. So how do we find left hand differential? So f dash x at any point, say x equal to a, from the negative side equals to limit h tends to 0 f of a minus h minus f of a upon f of x minus h upon f of x, or f of a minus h upon h. This is the left hand derivative. This is the left hand derivative. Similarly, f dash x at x equal to a plus will be limit h tends to 0 f of x plus h minus f of x upon h, right, at x equal to a. This is the right hand derivative, right? This is the right hand derivative. So first thing is that you should know about this continuity is necessary condition for differentiability. What does it mean? That only if a function is continuous, then it can be differentiable. If a function is not continuous at a point, we can never define differentiability at that point. So this continuity is a necessary condition, that without necessary condition, we cannot get what we want. Okay. The second thing is, it is not sufficient. It is not sufficient. That is, or we can say that converse is not. Converse is not true. What do you mean by converse is not true? That is, even if a function is continuous, it does not mean differentiable. So that is, differentiability implies continuity. We'll prove this also. But continuity does not imply differentiability. That is, even if a function is continuous, it does not mean it will always be a differentiable function. But if a function differentiable, then it will always be continuous. Okay, let's prove this. To prove that differentiability implies continuity. What will be the proof? Proof will be, let's say, at x equal to c, f dash x at x equal to c can be written as f dash c is equals to h tends to 0 f x, let's say, plus h minus fx upon h. Okay, and this at x equal to c. We know this, right? Now I want to check if it is continuous or not. If I can, if somehow if I get that limit x tends to c, f of x plus h minus f of x is equals to 0, then I can show this, right? Because that will mean that when h tends to, well, h tends to 0 at x equal to c, you can show that. Okay. So what I will do is I will take f of c plus h minus f of c on h, h tends to 0, and then multiply it x minus c and divide it by x minus c. You can do that. You can do that, and then this will be. Let me rewrite it. Becoming very, conventions are becoming very dirty. Let me rewrite it. So we need to prove differentiability implies continuity. Let's think proof. So let fx be the function differentiable at x equal to c. Okay. Let fx be the function differentiable at x equal to c. Okay. So f dash c exists, and is finite, and f dash c is equals to limit x tends to c f of x minus f of c upon x minus c. I have eliminated the h part. This can be written in this way. Okay. Now fx minus fc can be written as fx minus fc upon x minus c into x minus c. Take limit both sides. Limit x tends to c fx minus fc is equals to limit x tends to c fx minus fc upon x minus c into x minus, right? This can be, because this is also finite and this is also finite, so we can separate the limits. Limit x tends to c fx minus fc upon x minus c into limit of x minus c, right? X tends to c. So if you, this can be written in the f dash c, and this will be c minus c is equals to 0. So from here we have got that limit of x tends to c fx minus fc is equals to 0, which means fx is equals to fc, and that is function is called fx is continuous at C. Continuous at C. So this is the like you can write the proof in this way. You can write it in a much better way. This is very rough draft, but you get the point. And if a function is differentiable, if a function is differentiable, it means it will be also continuous at that point. So let's say if I give you a function and I don't say that it is continuous. So the step one should be check if it is continuous. Check continuity, then only proceed after that to check differentiability. Okay. So first you check if the function is continuous or not. Only if that function is continuous, then you will proceed to check the differentiability. Let's say you check continuity and it is not continuous, then you can directly write because the function is not continuous. Because the function is not continuous, it means it can never be differentiable. Okay. It can never be differentiable. So that is the first thing you have to do. Check continuity and then only proceed after that to check the differentiability. To check the differentiability. Okay. So this is the thing. So what we learned is first that continuity is necessary condition for differentiability. Necessary condition for differentiability. So that is differentiability implies continuity. Please mute your mic. Okay. And but the converse is not true. That is continuity does not imply differentiability. Okay. An example being in point is mod x. If you see function mod x, if you see the function mod x, then mod x is actually mod x is continuous, right? Everywhere is continuous everywhere, but not differentiable at x equal to 0. It is not differentiable at x equal to 0. So mod x can be a very simple, very easy function, which is like continuous but not differentiable. Okay. So if you read the book in the Madhikana rule, you will find a very beautiful function which was given by the mathematician Weierstrass himself. Okay. The function is fx is equals to sigma n equal to 1 to infinity 1 by 2 to the power n cos of 3 to the power n x. Okay. And this function fx is everywhere continuous but nowhere differentiable. Nowhere differentiable. The proof of this function is beyond our syllabus, but you can see that very beautiful function. That this function is everywhere continuous. It is in each and every point. It is continuous, but is nowhere differentiable. Okay. This is a very unique function in that sense. Can you give a function which is nowhere continuous? It is not continuous at any point. Anyone, like a function which is not continuous at any point. You have studied that function. Okay? You have studied two.
The Dirichlet function.
Yes. Good. So if you take the Dirichlet function, that is, if I take, let's say, fx is equal to 1, if x is rational, minus 1 if x is irrational. This function is not continuous at any point. It is always discontinuous. Always discontinuous. Okay. Now, if I want to create a function which is continuous just at just one point, okay, so I can modify this function. I can modify that function, and I can write it as x minus x. Okay. Then when x is rational, x is irrational, this function will be continuous at x equal to 0. At x equal to 0, this function will be continuous, but at all other points, this function will be discontinuous. Okay, let's say I want to create a function which is continuous at x equal to 1 by 2, but discontinuous everywhere. Discontinuous everywhere. Can you create such function? Take this as a task. Continuous at x equal to half, but discontinuous everywhere else. Okay. So take this as a homework question and do it by tomorrow, or else I will post the solution tomorrow in the evening. This is a very easy question. As a hint, this will also use the Dirichlet function. Dirichlet function. So you should remember Dirichlet function and you should learn to use it, because it can be used as hundreds of counterexamples. Okay. Whenever a counterexample is asked in real analysis, this will be very handy, very handy. Okay. Like for example, we know that if f is continuous, g is continuous. Okay, g is continuous. Then fg is also continuous, right? But if any one of these are not continuous, okay, let's say f is discontinuous, and g is also discontinuous, Can you find a function f into g which is continuous? Can you create such function? Yes, I can create it. If I define f as a Dirichlet function 1 0, okay, where x is rational, x is irrational. Okay. Now define g as 0 1. Same conditions. So f into g will come out to be 0, a constant function, right? Constant function. Constant function is always differentiable and always continuous. This is a very easy function. Very easy function. Similarly, like you want to show that f and g are discontinuous functions, and you have to create a function f plus g which is continuous. Take f equal to something, a discontinuous function, any function, and take g equal to minus f. Then f plus g will come out to be 0. Right? You can, if you are not comfortable at 0, you can create minus f plus 1. Then it will be 1, a constant. You can create any constant, and you can create such function f minus g. Same case, you can take g equal to f minus 1 or g equal to f, and you will get a constant. Okay, constant is differentiable, and it is also integrable. So these are very simple counter examples you can create on the board, so that you don't have to remember these counter examples. So functions like Dirichlet function, Fourier function, they come very handy, very handy in this. Okay. So let's see some questions, okay, from the differentiability part. So let's discuss this one, mod x. I want to say that mod x is not differentiable at x equals to 0. This is the statement. Okay. So let us find the left hand derivative, LHD, which will be equal to limit x tends to from the 0 to the negative side, then fx minus f0 upon x minus 0 is equals to limit x tends to 0 negative side mod x minus 0 upon x minus 0. Now this is some number less than 0, so mod x will be equal to minus x, mod x equal to minus x upon x, which will be minus 1. So left hand derivative is minus 1. Now let us find the right hand derivative. Limit x tends to 0 from the positive side, mod x minus 0 upon x minus c. Now because this is a mod x is positive, a little more than 0, so mod x will be equal to x. This will be x upon x is equal to 1. So here left hand derivative not equal to right hand derivative there at x equals to 0. Therefore mod x is not differentiable. I hope you guys are very intelligent, that I know. So many like young students like 8th class, 9th class, not 11th, 12th class, they ask if how we know that mod is always positive. Then why do we take a minus sign with mod? Okay, when x is less than 0 and greater than 0. So this minus sign we take because x is negative, right? Because if I want to take mod of minus 2, then minus of minus 2 is positive. That's why we take the minus sign. Okay. Now let's take another question. Fx is equals to x square sine 1 by x. X is not equal to 0 and 0 if x equals to 0. Okay. Can you guys solve this if this is continuous or not continuous?
This is continuous.
Yes, this is continuous because if I take mod x square sine of 1 by x minus 0, okay, less than epsilon, we can prove, I can get an epsilon because this will be x square of sine of 1 by x mod will be less than or equal to mod of x square. The mod of sine of anything is always less than equal to mod of x. So if delta is equals to x minus 0, that is mod x, then epsilon you can take equal to delta square, and you can prove it using the epsilon delta, right? This is very easy to prove. Now I have to show that it is derivable at x equal to 0. This is the first example number 4 in the book. It is derivable, but it is not equal to f dash x. And I also need the reason from that why it is not equal to f dash x. So if I find, let's say, f dash x will be x square into sine 1 by x. So x square is 2x sine 1 by x. Then x sine 1 by x minus so it will be x square cos of 1 by x into minus 1 by x square. So 2x sine 1 by x minus cos of 1 by x f dash x. But if you see, f dash 0 does not exist, right? dash 0 does not exist because we cannot find this cos of 1 by x. Here there is no problem because it is multiplied by 0 and it will give 0 because sine is always a finite value. But I cannot find this value. So I can't determine the value of f dash 0. But it is saying it is derivative, that we can find the derivative. Okay, we can find the derivative. How can we find the derivative? Let's see. So I want to find, let's say, f dash 0. It will be equal to limit x tends to 0, f of x minus f of 0 upon x minus 0. Now, limit of, I'm not taking left hand right hand limit because for all the values, if you see, okay, for all the values x not equal to 0, be it positive or be it negative. So if I take x minus h or x plus h, I get the same function. So I don't need to evaluate both the limits. I can take just one limit. This will be x square sine of 1 by x minus this is 0 upon x is equals to limit x tends to 0, x of sine of 1 by x, right, which is equal to 0. So both the left hand derivative, okay, both the left hand derivative and the right hand derivative will come out to be 0. Okay, but f dash x, okay, f dash 0 does not exist. That is, if we directly differentiate this function, then it will give us a wrong value. And lot of people do this mistake in the exam also. Let's say if it is it asks you to find the value of f dash 0, you cannot directly differentiate this. Okay, you have to go by the definition, and this happens a lot during when you guys will study complex analysis now. So there is a question of CR conditions, okay, Cauchy-Riemann conditions. So there they will give you a piecewise function and they will tell like ask you to prove that CR conditions hold, but still it is not differentiable. So a lot of people directly differentiate the piecewise function, which is wrong. You have to go by the definition in some cases. So this is the question. I think only 10 minutes are left in the meeting. So I will schedule another meeting because I have to discuss 1 to more concepts with you. Okay. So this is the thing. Do you guys have any like question or any issue? So you guys have to practice this, that f and g are differentiable functions, then f plus minus g is also differentiable, f into g is also differentiable, and also find the differential coefficient or differential, like what is the relation, and f by g is differentiable if provided g is not equal to 0. Try proving this. Okay, I will like give a hint how to like go about it. Let's say I have to prove that if f of c is not equal to 0 and f dash c exists, prove that 1 by f of dash c is equals to minus f dash c upon fc square. So this is the thing that so I know that f dash c is equals to limit x tends to c fx minus fc upon x minus c, right? This is the thing. Now, so 1 by f dash c is equals to limit x tends to c 1 by fx minus 1 by fc by x minus c. S is equals to limit x tends to c fc minus fx by x minus c into 1 by fx into fc. We know that fx is non-zero, that fc is non-zero, and fx is continuous because it is, if it is differentiable, then it has to be continuous. So from this, I know that this is minus f dash c. Okay, this term is minus f dash c. This term is minus f dash c, and this will be 1 upon fc into fc. This will give me f dash c whole upon f of c square. Okay, so these are very straightforward proofs that you can easily do. Okay, so what kind of questions will come in the exam? The questions will come the same as the kind of question that come in the uh, form of continuity. Okay, that you will be given a function. For example, you will be given fx is equals to, okay, x of, let's say, tan inverse 1 by x when x is not equal to 0, and 0 if x is equal to 0. And you have to show that, or you have to find the left hand derivative, okay, the right hand derivative, okay, left hand derivative and the right hand derivative, and show that if it is differentiable or non-differentiable. Okay, like another question given in the book is like this: x into e to the power 1 by x minus 1 whole upon e to the power 1 by x plus 1. These kind of limits you have already found in the previous chapter, like when you were studying limits and when you were studying the differentiability part, right? So you just have to apply that knowledge in this. So the questions are not any like they are not unique. They only employ the your knowledge and your like practice of limits. Okay. So I'm booking the I'm generating another link for the meeting, and in that we will solve five, 6 good questions, and then we will move to discuss what is increase and decreasing function and all those things. Okay. So I'm ending this meeting for now, and I'm sharing the new link.
Okay, sir.